31 people died in under a minute, not because of a bomb, not because of a structural collapse, but because of a fire that, by all accounts, should have put itself out. What investigators discovered over the next 7 months didn't just explain the King's Cross disaster, it rewrote the science of fire itself. November 18th, 1987. It's a Wednesday evening on the London Underground, and King's Cross Station is doing what it does every night, swallowing thousands of commuters whole. A Piccadilly line train pulls in, doors open, and the usual flood of passengers pours onto the platform and heads for the escalators. Coats, briefcases, the distant smell of cigarette smoke. Just another night. Then someone notices a faint orange glow flickering beneath one of the old wooden escalators. Small, almost nothing. A passenger mentions it to staff. Staff call the fire brigade, and at this point, nobody is particularly worried because this has happened before. In the 30 years leading up to that evening, more than 400 small escalator fires had broken out across the London Underground. Every single one had either burned itself out or been dealt with quickly. This would be no different, except it was catastrophically different. When firefighters arrived 10 minutes later, they found what appeared to be a manageable escalator fire. Small, contained, nothing unusual. And then, without warning, in a matter of seconds, the entire escalator erupted. A jet of fire blasted upward into the ticket hall. By the time it was over, 31 people were dead, dozens more were injured, and investigators were staring at a scene that made almost no sense. Here's the thing about fire investigation. It's essentially forensic archaeology. Fires don't erase evidence. They leave it everywhere if you know how to read it. Fire burns upward and outward, so when something ignites next to a wall, it leaves a distinct V-shaped burn mark, with the point of the V closest to where the fire started. If the object is slightly further from the wall, the shape opens up into more of a U. Investigators read these patterns the way a doctor reads an X-ray, treat systematically, carefully, looking for what the damage is trying to tell them. They also look at char. When materials burn, the water and organic compounds inside vaporize, leaving behind a layer of carbon on the surface. The longer something burns, the deeper that char goes. So by measuring char depth across similar materials at different points in a space, investigators can essentially build a timeline of the fire, figuring out which areas ignited first and tracing the path backward to the source. In most fires, this process leads somewhere clear, but the King's Cross fire wasn't cooperating. Eyewitness accounts were deeply strange. Survivors described the fire not burning upward the way fire is supposed to, but burning at an angle, almost perfectly horizontal, hugging the surface of the escalator steps. Fire doesn't do that. Hot gas rises always. That's not a guideline. That's physics, and yet multiple witnesses described exactly this behavior, with the flames pressing themselves flat against the escalator rather than rising towards the ceiling. Investigators opened up the other escalators in the station and found something grim. Years of accumulated grease packed with dust, fabric fibers, and debris that had dropped through the gaps during decades of operation. Tests confirmed that a lit match falling through the escalator gaps could easily ignite this mixture. That explained how the fire started, but every time they tested it on an open model, the fire burned straight up and eventually died out on its own. Something else had to be happening inside the actual escalator shaft, and they couldn't figure out what. 7 months into the investigation, they turned to the most powerful computational resource available in the UK at the time. The Cray 2 supercomputer. There was only one in the country. Researchers used it to build a simulation that could model temperature and airflow at thousands of points throughout the escalator shaft, trying to understand how gases and heat would actually move inside that enclosed, angled space. The results stopped people in their tracks. The simulation showed something that had never been documented before. Because of the unique geometry of the escalator shaft, its narrow, trench-like structure, and its 30-degree incline, the fire couldn't spread outward the way it normally would. Instead, the heat was forced to travel in the only direction available, up the trench along the floor of the escalator. As the hot gases accelerated up the shaft, something unexpected happened at a fluid dynamics level. Their speed increased, and as speed increased, pressure dropped. This created a pressure difference above and below the escalator steps, and that difference gradually tilted the fire, pulling the flames downward until they were pressing flat against the underside of the steps. The faster the fire burned, the more it accelerated. The more it accelerated, the more pressure dropped. The more pressure dropped, the harder the flames were pressed against the steps. It was a self-reinforcing cycle, and it had a devastating consequence. From the outside, standing on the escalator or looking up from the bottom, the fire looked small, manageable, unremarkable. But beneath the steps, hidden from view, superheated gases were cooking the entire length of the wooden escalator, hundreds of degrees above the threshold at which materials spontaneously ignite. Those same gases were funneling up into the ticket hall and accumulating in the void above the false ceiling, invisible and undetected, heat building with nowhere to go. And then it hit flashover. Flashover is the moment when the temperature in a space reaches the point where every combustible surface ignites simultaneously. It doesn't creep, it doesn't give warning. 1 second, there's a fire in one location. The next, everything is on fire at once. The escalator, the ticket hall surfaces, the accumulated gases above the ceiling, it all went in an instant, and the fireball that followed killed 31 people in moments. When investigators built a physical scale model of the escalator shaft and tested it in controlled conditions, they watched the same thing happen in real time. The fire started vertically, just as it always had in open tests. Then, gradually, it began to lean, and then it lay flat, hugging the floor of the trench exactly as the simulation had predicted. They had their answer. This phenomenon, completely unknown to science before that night, was named the trench effect. It has since been incorporated into fire safety standards and building codes around the world. In the aftermath of King's Cross, every wooden escalator on the London Underground was replaced with metal. Heat detectors were installed beneath escalator structures, connected to automatic sprinkler systems, staff received emergency training, smoking bans were enforced with real consequences. An entire category of fire risk that nobody knew existed was identified, studied, and systematically addressed, because investigators refused to accept "we don't know" as a final answer. 31 people died because of a fire that should have been nothing, but in trying to understand why, scientists and engineers uncovered a piece of physics that had been hiding inside every angled underground shaft in the world, waiting for the exact right conditions to become catastrophic. The King's Cross fire changed how we think about enclosed spaces, airflow, and fire behavior in ways that have almost certainly saved lives in the decades since. Lives that were protected by safety standards written in the language of that investigation. If you want more deep dives into the science and engineering behind some of history's most consequential disasters, subscribe. There's a lot more where this came from,